do some of these. So you probably haven't finished this worksheet yet. Probably no one has. I'm going to show you, though, some of the things about it so that finishing it up will probably go easier for you. So I'm going to share a copy of this right here as a Word document. You able to see the Word document?
Yes.
Great. Okay. Well, we had those 6 elements at the top. Those are the ones that are kind of tricky. If you see something where, for instance, it mentions element Fe, you should know that that one is what?
Iron.
Iron, exactly. The others are similar. The first one here, K, is what?
Potassium.
Potassium. See, these all have symbols that don't necessarily match with the names. I mean, Ca it matched with calcium. It could also look like carbon, and so you need to know which is which. This one is calcium. This one is magnesium. Here we have, phosphorus. That is element P. So that would be easy to mix up with the potassium, but potassium gets the letter K, and so on. Then, if we're talking about molecules, we always write a molecule with a molecular formula that goes like I have here with H2O. If you have, say, several atoms joined together in one collection as a molecule, we'll just write it out telling how many there of each element there are in the molecule. In this case, 2 H's, write that as a subscript, not a superscript. It goes as a subscript right after the H, followed by O. Means 2 hydrogens, 1 oxygen. If you have 6 of those water molecules, then you put the 6 in front. That's a coefficient. So how many oxygen atoms do we have with 6 H2Os?
6.
Yes.
6.
How many hydrogen atoms?
12.
Well, yep. Then when we've got a chemical reaction, normally there's an arrow goes in, and that shows that we've got a transformation going from reactants to products. Sometimes they'll have the arrow going both ways, but usually we think of it this way. Having, for instance, elements left of the arrow, or the molecules left of the arrow, being transformed into the molecules at right. Now, if you count it up, you find the same number of atoms of each type on both sides, because a normal chemical reaction is not destroying atoms, it's not making new ones. What it's doing is rearranging them. So we have different partnerships, different pairings of things. But if you look at it, you have, for instance, 6 carbons over here, and the same 6 carbons show up on the right. So we have reactants, left side of the arrow, products on the right side. And I asked you how many of these different kinds of atoms were among the reactants. I could have easily said as among the products. I just, either way, I was specifying on one side so we're not double counting things. How many hydrogens, oxygens, and carbons do we have here?
12 hydrogen.
12. Oxygens?
18.
That's 18.
And
6 times 2 and 6 plus 6 times 1. Carbons? 6. Here's the part that often trips people up. How many molecules are on this side?
12.
Yes, 12. People often come up with 36, and I think what they're doing is counting up all the atoms. But this is saying 6 carbon dioxide molecules plus 6 water molecules.
Wait, how do we count the oxygen again?
Okay. Each CO2 molecule has 2 oxygens in it. So there's 6 CO2s, that means 12 oxygens in there, plus each water molecule has 1 oxygen, and there's 6 of those molecules. 6 times 2 plus 6 times 1 comes up to 18.
Okay, thank you.
You're welcome. Now I asked you to complete this table, and, well, obviously that's kind of tricky. There's enough information here to answer in all the blanks. If you're assuming equal numbers of plus and minus charges. which is what I say to do here. I gave you one of them worked out completely. That's the carbon 12. Now notice the atomic number is the same as the number of protons, and it's the same as the number of electrons if we have equal pluses and minuses. It happened in this case to be the same as the neutrons, but that's not always going to be the case with these. But if you know that this column, and that column are all the same, then you've got enough information in every case to work them out.
Yeah.
We know what the symbol would be for nitrogen. It would be what? N, yes. Should know that one, that one, that one. And then with some, you have to work backwards to figure out what the element is. Make sure in every case you're giving me a number so that each of these specifies which isotope we're talking about. There's enough information in each of these, though, to fill them out. Remember that protons and neutrons add up to the mass number. And if you know the atomic number, you know the number of protons and the number of electrons. Any of those can lead to the others. Then we've got three different things where we're talking about the shells. Some of these will be zeros or just blanks. And the last part, we're thinking about ions. You know from the atomic symbols what the elements are and what the number of protons have to be. Then you can figure out the number of electrons in each case to give a positive charge, a negative charge, or a double positive charge. That's what happens with Ca2+. All right, do you have questions for me here?
No.
Yes. So for the isotope name, for like let's say the one where it says atomic mass 23,
Yes.
you want it to be like sodium-23?
Yes, you're right on both of those. Yes, that's exactly how I want you to do it, following the format that I already gave you. And that is the right answer for that one. Good job.
Same thing with iron for the bottom one.
It is iron, yes.
Just leave it as iron since there is no atomic mass there.
You gotta figure it out.
Iron.
Gotta figure out that mass. So you want to match the format here.
What was the answer
There's enough information in every case to work it out. Someone was starting to say something?
What was the answer to the last question of number 3? How many total molecules?
Okay, let's look at that again. Looking at the products, so the produce, on the right side here, we have 6 of these and 6 of those. I'll just make one right now. I have a model kit here, and I'm going to be using this in a few minutes to show you some stuff. But for instance, there's a water molecule. I'm hanging on to the oxygen, and then we have these 2 white hydrogens. So this molecule is a fairly stable thing, and there are 6 of these in that reaction that I show on number 3. 6 in the products. 6 of those, and 6 of this other kind of molecule.
Thank you.
Okay. Well, then I'm going to leave you to getting this worked out and turned in. And again, to turn it in, go into the assignments section on Canvas. And there's a place there to upload this assignment, which is similar to what you did with some assignments from last week. Well, let us go and look a little more here at chemistry. So, what do we get? We get what are known as chemical bonds. Those are connections between the atoms that go into these molecules. And so what will happen is, for instance, in this case, I've got 1 oxygen bonded to 2 hydrogens. That has to do with sharing of electrons between these atoms. There's 4 kinds we're going to look at. Your book talks about a 5th one. I'm not going to go into it. But we have ionic bonds, which are probably the easiest to understand. Then we get covalent bonds, and there's different versions of those, non-polar to polar. And then the trickiest ones to understand will be the hydrogen bonds. Those are the weakest of all the bonds that we look at, but they're very common and they're very important. So to understand these, we're going to work up in this order. Then your book refers to what are called van der Waals bonds, but I'm not going to go into those. The covalent bonds, the different kinds of them, are strong, and they're the ones that we're looking at. If we see a molecule like this, everything we're looking at here with all these sticks represents 1 or even 2 covalent bonds. So when you're looking at a molecule, the way it's usually diagrammed is by showing the covalent bonds. Those are the strongest of the bonds. When it comes to ionic bonds, well, again, those are the easiest to understand. You have, say, an element that ionizes, like sodium. As we saw, it wants to go into the ionic form, and chlorine does the opposite thing. It wants to go into a negatively charged ion. The sodium becomes a positive ion. Chlorine becomes a negative ion because sodium has this situation where it has 1 electron in its outer shell that it's trying to get rid of. You saw how aggressive that is when we saw the sodium metal explode or sort of explode in water. That was from the sodium metal trying to get rid of this electron. Chlorine has exactly the opposite problem. Chlorine has 17 electrons, so it's got a 2 + 8 + 7 arrangement with its shells, and it's aggressively trying to fill up that outer shell by stealing an electron from somewhere, or maybe just finding one that's lying around. So if you put these 2 together, it's a perfect match. Sodium wants to get rid of an electron, chlorine wants to absorb one. So chlorine takes this electron away from sodium, and now we have a positive ion and a negative one, and they want to stick together. So in a salt crystal, what we get when we remove water from seawater is we get all these ions sticking together. And sodium and chloride form this cubic arrangement where you have this alternate stacking of positive and negative ions. And they stack together forming little cubes, which is what salt crystals are. If you're using a salt shaker, you magnify those little grains of salt, they're little tiny cubes. And so each of these forms from the stacking arrangement of these ions. They stack up like this so that each ion is surrounded by ones that have the opposite charge. They're all happy that way. So these ions are ionically bonded to each other, positive ion bonding to a negative one. That's what happens in salt crystals or rock salt underground. In the seawater, these cubes, say, would dissolve, and you get the ions floating separately surrounded by the water, which is something we will see later how that works. But that's ionic bonding. Questions for me on that?
No.
Okay. Well, the ionic bonding like this, it'll stay this way till the end of time as long as you don't add water. So we get rock salt deposits that have been underground for millions of years. Then if you put it back into the ocean, it'll dissolve and then stay that way till the end of time. But the covalent bonds, these are the more important ones. And what we're getting here is a sharing between 2 atoms. They're sharing pairs of electrons. When that happens, let's say if we have, for instance, an oxygen and a hydrogen, and they enter into a bonding arrangement. What they do is they share 2 electrons. Each one of them contributes one of the electrons to that shared pair, and we end up with something like I'm indicating here. The stick represents 2 shared electrons between these 2 atoms. One of the electrons came from each atom, and together that becomes a stable sharing arrangement. And each atom effectively picks up another electron in its outer shell. So this hydrogen by itself just had one electron in its outer shell, but if it shares, now it effectively has two in its outer shell. That's what these two in the bond will basically give this hydrogen a more stable arrangement, where it has now two electrons that are in close to its one proton. And here's what happens. Carbon is able to form 4 of these sharing arrangements. Nitrogen forms 3 or sometimes 4. Right here we're just going to say 3 covalent bonds. And that means carbon is forming bonds with 4 other atoms, potentially, sharing 4 pairs of electrons with 4 other atoms. That means carbon is really versatile at building things like this organic molecule I keep showing you. All those black atoms in here are carbons, and they are able to form bonds 4 different directions to other atoms. So carbon is extremely versatile at building these complex molecules of life. Nitrogen is also pretty good at doing that. Then oxygen can only form 2 covalent bonds. Hydrogen can only form 1. You need to know these numbers. This is something to memorize. But as a result, 1 carbon atom can bond to 4 hydrogen atoms, and that forms methane. That's natural gas. So if you were, for instance, using methane, maybe or using natural gas with your stove this morning, maybe heating up some water, the natural gas is what methane is. And I'm building it right here. So here, CH4 methane. This is what is basically a natural gas. And in this case, this satisfies the bonding rules. What we have here, we know that carbon can form 4 bonds. Well, there it is at the center, bonded to 4 other things. And we know each hydrogen can form 1 bond. There, each of them is forming 1 bond right back at the carbon. This satisfies the bonding rules. Something like CH8 would not, because carbon could not bond to 8 other hydrogens. CH2 would not, because carbon would be desperately looking for 2 more things to bond to. CH2 would be kind of an incomplete molecule. CH8 would be just an impossible molecule. So we get certain kinds of molecules, and we don't get certain others. So we form this covalent bond, having 2 atoms come together. Each of them by itself is what we call a free radical. That means a single atom that is super reactive, looking desperately to form a bond with something else. And when 2 different hydrogens form this single H2, each hydrogen now has a full outer shell. Here, neither one of them did. You take 2 hydrogens, put them together, it releases energy and forms as H2. This is more stable. To break this apart back into 2 separate atoms, you would have to put that energy back in. Hit it with like a laser or something to bust this apart into 2 separate atoms. So there we formed a covalent bond, 2 shared electrons. Oxygen, same kind of thing happens, but it's more complicated. 1 oxygen atom by itself, how many electrons are in its outer shell? For 1 oxygen atom?
6.
6. Oxygen is element number 8. 8 protons, so if it has 8 electrons, then we get a 2 plus 8 arrangement, or 2 plus 6 arrangement. It has 2 openings in the outer shell. If you get 2 oxygens together, this is how they form that and fill up their outer shells. They form 2 covalent bonds. So I am going to make that one right here. Oxygen with 1 and 2 covalent bonds forming. And here I can form the double bond, and there I have it. That is O2. That's what you're breathing right now. The stuff that we really care about with breathing. This is what's keeping you alive. And so we get a double bond, 2 shared electrons and 2 shared electrons. Together, that gives each atom a full outer shell. So do you see that with the outer shell here? How many electrons are in that outer shell now? How many are out there?
8.
8.
Exactly. It would have been 6 with the single atom, but now it's 8. So if we look again at these electron configurations for these big 4 elements, the ones we care about the most here, you can see where the number of covalent bonds comes out. It basically has to do with how many holes are in the outer shell. Hydrogen has 1 hole, it forms 1 bond. Sharing 2 electrons fills up its outer shell. Oxygen has 2 holes, 2 bonds. 3, 4. Now we get covalent bonds showing up everywhere. Here's an example. You have what's known as a triglyceride fat, and we will see these later. This is what's in body fat, though, or like in oil, like olive oil. So the covalent bonds are all of the connections between these atoms, and they're showing a lot of those here as these little sticks. So the covalent bonds are supernumerous. You don't need to understand this structure yet. That will come later this week. More information than you need on that. But here's another one. Typical kind of an organic molecule, the glucose. And again, all of these sticks that are connecting the different atoms, including these very short ones here, all of those are covalent bonds. So, given that, we can make a few more of these molecules. Normally, I have these kits out in the classroom, kits that are something like what you're seeing here with this top of the box. These then have a lot of different kinds of atoms in them. Here's the contents of one of these boxes. All these atoms in there, and I'm going to use some of these to build others that we haven't already seen. Normally, again, I would have this in the classroom, but I don't have that arrangement, so I'm just going to have to show you. So, CH4, that is this one, methane. O2, I already made, there it is. 2 oxygens with a double bond between them. Water, oh yeah, water I was hanging on to with my other hand. There's a water molecule, H2O. The water molecules actually have this shape. They have a kinked shape. It's important for their behaviors. Let's see about others. CO2 is a pretty important one. Do we make any CO2 in our bodies?
Yes.
Yes, we do. So let's see if I can make it right here. Okay, is that CO2? Red is oxygen, black is carbon. So,
Yes.
yes or no? Oh, it's a trick.
Yes. Yes.
It's actually a trick question. You got the right number of atoms, but not the right number of bonds. How many bonds does carbon want to have?
4.
1. Well, right now it only has 2. How many does oxygen want to have?
2.
2. I just have 1. So we need more bonds. And so I'm going to put them in. What we need are some double bonds. I'm making those right now. Now we have it. This is a legal CO2, let's say. It has the right number of atoms, but also the right number of connections between them. So, how many bonds does carbon have there?
4.
4. And each oxygen has how many?
Two.
Good. Well, this is what you're exhaling. So this one goes in, this one comes out with every breath, every cycle of breath. Nitrogen, well, that one's pretty tricky. So let's take a look at nitrogen. And I think I've got enough of these. Yeah. I'm going to have to take something apart to get enough pieces here. Okay, we use these blue atoms for nitrogen, and how many bonds does nitrogen want to form?
3.
Yeah, so N2. Is that it right there?
No.
No.
Each atom wants to have 3 bonds, and that will fill up their electron shells. So I have to really get in here and bend these things a lot. Okay, I'm almost there, but actually it takes another one. There we are. This little thing. 3 bonds in there. So how many shared electrons? 6. Each atom put 1 electron into each of these covalent bonds. So 2, 2, 2. This is mostly what you're breathing right now. This is 78% of the atmosphere. And for us, it's an inert gas. It's not doing anything in our lungs. It's just taking up space. So that's the majority of what you're breathing, but the part that really matters for us is this one, the O2. This makes up 21% of the atmosphere. Nitrogen, 78%. Well, we've got that, and then there's that last one. And I wrote the formula in kind of a non-standard way, but in a way it's more descriptive doing it like that. So I'm building that one for you. And this is kind of fun. Yeah, so I got part of that together. Now I just have to put on some hydrogens. There it is. What I wrote as C2H5OH. Well, up here we've got the OH, we've got the 2 carbons, and 5 other hydrogens. What does this kind of look like to you?
It looks like a dog.
Yeah, I know it. You can actually make different breeds of dogs by using different connectors here, so kind of fun. But that's really what's especially interesting with this is alcohol. This is the standard drinking alcohol, ethanol, stuff people get drunk with. So it's a very simple formula, but this penetrates into the brain and obviously has pretty important effects there. Now, it's not the only kind of alcohol. We have another one called methanol that's even smaller, and that one is a deadly poison. This methanol, a smaller alcohol, this is the one that will attack the optic nerves and make people blind. So you do not want to be drinking methanol. But otherwise, the less toxic ethanol is something a lot of people enjoy drinking, obviously. And over thousands of years, we humans have gotten very good at making ethanol from all kinds of various plant products. For instance, what plant do we use to make rum with? Anyone know that? Try sugarcane. Think Pirates of the Caribbean. Or we use potatoes, say, to make vodka. Grapes, of course, to make wine. So we've gotten very good at doing these processes to make alcohol. And whatever kind of alcoholic beverage you're talking about, it's this particular thing that looks like the dog. So that's some of what we go into here. And again, in a normal class setting, I would have you making those models, but we don't have that option here. Now, here's the thing about covalent bonds. They're not all the same. They're forming because you have two atoms coming together, and each one is trying to grab an electron from the other atom. But then it's having to give up a piece of one of its own. And the thing is, some elements are better at grabbing the electrons or stealing them than others are. So if we put two elements together that are different, then one of them will have a stronger pull on those electrons than the other one. These electrons are being shared in a bond between two atoms. And the sharing could be equal or nearly equal, and we call that a non-polar bond. This is a very important piece of terminology for you to get to know. So if we have sharing that is completely equal, like for instance it is right here, we have two identical oxygen atoms. They're pulling exactly the same on the shared electrons. This one is totally non-polar. On the other hand, we have here water and oxygen, and they are actually extremely different in their pulls on the electrons. Oxygen here is able to pull the electrons much more toward itself. So oxygen with water gets negatively charged, and the hydrogens get positively charged because they lost some of the control over the electrons. This is going to be a very important concept to get straight. So there is a tug of war going on between atoms in the various situations that we see here. And we use this thing called electronegativity to say just how strongly each atom is pulling on the shared electrons. And it works like this. You will not need to know the numbers, but you need to know this hierarchy, this ranking. Oxygen is the strongest at pulling on the electrons. Hydrogen is the weakest. Nitrogen and carbon are intermediate. So when we see bonds like these, we have shared electrons. And for instance, over here we have some shared electrons. And right here, we've got a very unequal sharing going on. Now here, in the middle of this, between the two carbons, there's totally equal sharing between them. And between the carbon and the nitrogen, or hydrogen, they're almost equal. So we've got some nonpolar bonds going on in this part of the molecule, but up here, we have polar bonds. And that causes a really important behavior in this area. So if we have something with oxygen paired with hydrogen, we get what we call a polar covalent bond. That means it's a charged bond. The bond has a positive end and a negative end. So in that case, if we have this polar covalent bond, oxygen gets negatively charged. It's pulling the electrons away from that hydrogen. The hydrogen ends up having a positive charge. Are you with me on this so far?
Yeah.
This will be one of the trickiest things to get straight. We'll be using these terms polar, nonpolar a lot. So when you're looking at a water molecule, it has two polar covalent bonds within it in one water molecule, like in the diagram. We have oxygen sharing electrons with a hydrogen with another hydrogen. And in each case, the electrons are being pulled in toward the oxygen because it has a stronger pull. The hydrogens are losing the electrons, and they're getting a little bit positive. So oxygen negative, hydrogens are positive. So water molecules have a negative end and two positive ends. And as a result, they form hydrogen bonds with each other. mentioned we would be getting to these things called hydrogen bonds. And that is where we have a weak bond forming between two different atoms, because we have areas on the atoms that are positive or negative, and the different atoms will then be attracted to each other at these different spots. Like in this case, two waters, positive hydrogen here goes to negative oxygen there. They want to stick to each other. That's a hydrogen bond between these two water molecules. Or it could turn around the other way, and we could have this positive hydrogen go to that negative oxygen, like this. These are hydrogen bonds. Those are weak attractions. They're not nearly as strong as a covalent bond, but they're very common. You get a lot of them going on, and so they have importance just by sheer numbers. If you're looking in liquid water, typically each water molecule forms 4 hydrogen bonds with its neighbors. So the water molecules are all sticking to each other. These bonds are constantly breaking because in a liquid the molecules are moving from place to place. But every time one breaks, another one forms with some other molecule that moved into the position. So water molecules are constantly sticking to each other. So within one water molecule, what bonds do we have?
A polar covalent bond?
A bond? Is it one bond?
2?
2. Yeah, here's one water molecule with the sticks representing the polar covalent bonds. Polar means that this bond is polarized with a negative end and a positive end. And that makes this molecule sticky to other polar molecules because the polar things basically are attracted to each other, with negative being attracted to positive. And so this water molecule is going to be attracted to other water molecules. They want to cohere, they want to stick together. Then hydrogen bonds, the weak connections form between the different molecules. So you have the polar covalent bonds, which are, say, permanent or sort of. The hydrogen bonds are constantly changing, but they're always there. There's other ways to get hydrogen bonds. If you have, for instance, something like our alcohol here. If you think about alcohol, does it dissolve in water?
No?
What about that? If you have a glass of wine, say it has 14% alcohol, what's the rest of the liquid?
Water.
Water. It's water. It came from grape juice. So actually, alcohol dissolves just fine in water. Dissolving means that the water molecules are attracted to the alcohol. So right here, I have an alcohol, ethanol molecule, and it has this polar region, and this is acting like half of a water molecule. That means water molecules can come in and try to stick to that, like I'm doing there, positive to negative, or positive to negative, like that. So there will be several water molecules surrounding this part of the alcohol, forming covalent or hydrogen bonds with it. As a result, alcohol, typical drinking alcohol, dissolves just fine in water. So any place where we've got polar covalent bonds can form hydrogen bonds with other things that are polarized. So I'm going to skip by the language here and go to the diagrams. So right here we have a place where hydrogen bonds come in with DNA molecules. Well, that's something we'll look at some later in this week. But hydrogen bonds are important in holding DNA molecules together. And again, I'll skip that. And let's think about properties of water. And then I'm going to give you guys another thing to work on. So imagine we're taking a water molecule And it's again like what I'm holding here, where we have the red oxygen, the white hydrogens, oriented the same way as in this diagram. Positive hydrogens, negative oxygen. You combine those with, say, a salt crystal. What happens to the salt? If you take salt crystals and throw them into a pot of water, what happens to them?
Dissolves.
Dissolve. Yeah, that means that these ions come apart and they float around separately in the water. And the way that happens is that each ion becomes surrounded by water molecules. You have the sodium ions, and they have a positive charge. They're very attractive to the negative ends of the water molecules. The negative part of the water molecules attracted to the positive sodium. And then the same thing happens with the negative chloride molecules. But what's different about the water over here?
The oxygen's being attracted to it, like the positive charge.
Yeah, that's actually the hydrogen. Yes. Yeah, so see, the water molecules can flip around either way. They're able to dissolve the sodium and the chloride just by facing the opposite ways. So that we always get opposite charges being attracted to each other. So what happens if you put a salt crystal into water? It breaks apart and the individual ions each get surrounded by a shell of water molecules. And this is how it is in seawater. And it'll stay that way forever unless you evaporate the water out. Then you go back to having the salt crystal. So water is good at dissolving stuff. Water is a really good solvent. That's one of the key aspects of it. But salt crystal falls apart. Each of the ions gets mauled by water molecules. And again, just notice the water molecules face in opposite directions. So with the sodium, this is what we're getting. Technically, this is more accurate because I've just been saying plus or minus, and really it's a little bit positive, a little bit negative. That means that the plus charge is not a full proton's worth, and the minus charge is not a full electron's worth. But fundamentally, this is still the same as that. So water, it becomes an excellent solvent of things. Solvent is whatever dissolves solutes. So anything that is a very polar substance, like the salts, will dissolve in it. Also sugars. Glucose, say, dissolves just fine, and I'll show you why. Glucose is acting a little bit like alcohol. Glucose has a lot of these OH units. And again, when you've got this OH, there's a positive end and a negative end. So water comes close to being a universal solvent. An actual universal solvent would dissolve anything, and nothing does that. We would have trouble storing it if there was such a thing. It would eat through the container and just start eating down into the earth. But water does a pretty good job. The thing it will not dissolve would be fatty or oily substances. So if you think about how, like with the salad dressing, how the oil and the water parts separate, that's effectively where water hits its limit. So there are some things it can't dissolve. And that actually is essential for how cell membranes form. We'll be seeing that in days to come. So do you have questions for me on this at this point? Okay. I'm sure your brains are getting full. We'll do a little more of this looking at properties of water. Then I'm going to give you a thing to work on with that, not for credit this time. Following that, we get to see some stuff changing color, and you'll go, ooh and ah. But here's my example with the glucose. Here at the center, That's the glucose molecule. And this is the basic blood sugar in our bodies. If you are running an excessively high glucose level, maybe you have diabetes, but otherwise everybody has glucose in their blood. You would die without it. And you can see how the glucose can easily dissolve in water, like, say, in a watery material like cytoplasm or in your blood plasma. Each of these OH units there's 5 of them on the glucose. Each one of those is extremely polar, acting like half of a water molecule, so they attract water just the way water would. Each glucose gets surrounded by a shell of waters, similar to what happened with the salt. So, just the way salt dissolves in water, so does glucose. And again, ethanol dissolves in water, which is why you can have, say, beer or wine, and there's alcohol in most of the water. So water is good at dissolving stuff. It also keeps a stable temperature. What that means is that it has a high heat capacity. What that means is it's able to soak up a lot of heat energy without its temperature changing very much. So that allows it to keep a stable temperature, comparatively stable, even if a lot of energy is going in or out. Water's temperature doesn't change very fast. That's part of our homeostasis in our bodies. The fact that our bodies keep close to a stable temperature, even though the external environment changes, has a lot to do with us being mostly made out of water. And that's because of all those hydrogen bonds. Remember, each water molecule has about 4 bonds with its neighbors, and it's a whole network of these connections that are able to absorb energy, a large amount of energy, without the water molecules really moving much faster. And temperature is an expression of how fast the molecules are moving around and banging into stuff. If you put your hand into super hot water and it hurts, it's because these water molecules are banging into your hand very rapidly. And the hydrogen bonds tend to prevent that temperature from increasing or decreasing very rapidly. So water keeps a fairly stable temperature. Compared with rocks or metals, its temperature is about 5 times more stable. So if you were made out of rock, you would run a fever really easily. Or made out of metal, maybe you would get super cold really easily. You're mostly made out of water, and your temperature stays stable. It's because of this whole network of the hydrogen bonds that are in here. In this diagram, we've got the dashed lines. Those are hydrogen bonds. Then we have the covalent bonds within each water molecule. The hydrogen bonds are connections between different water molecules. Well, keeping the stable temperatures is essential for our chemistry to behave properly in our bodies. We have these molecules called enzymes that guide along our chemical reactions, and they have optimal behavior depending on what the temperature is. Basically, our enzymes work best at body temperature, 37 centigrade, and if we get too cold or too hot, they don't work as well. The fact that we keep a stable temperature is essential for our enzymes to work correctly and for life to exist. Then water molecules stick to each other. They cohere. That's what happens when they're sticking to each other. They also adhere to a lot of other things. That's water sticking to other substances. That's important for like movement of water up a tree. In water movement in a tree, we have water continually being pulled up and pulled, basically the leaves pulling it out of the soil, up through the roots, into the leaves, and evaporating into the atmosphere. That involves a lot of this cohesion. So right here, if you put water into a typical graduated cylinder, notice how it climbs up the edges, climbs up the sides. What's going on there? Cohesion or adhesion or both? What do you think is going on?
Both?
Yeah, actually both. The water is clinging to the sides and trying to climb up, and then it's pulling other water up behind it, which we can see right here. So the water is clinging to the glass, say, and clinging to other water molecules. That is showing us both right there. Water forming drops, having surface tension, so some spiders and insects can walk on the surface, moving through trees. It's all having to do with water cohering. And ice floats. This doesn't happen with everything. If you have, say, molten rock, like in a volcano, molten magma, it cools off at the surface and gets where it's not glowing anymore, and that surface material sinks. Rock, when it cools off, gets more compact and denser, and it sinks. Same thing with metal. If you're in like a steel mill and there's this big vat of molten steel, right on the surface, it's cooling off on contact with the air and then sinking because it's condensing, getting a little bit more compact and sinking to the bottom. Most things do that. Ice does not. Ice floats. That means that 1 cubic meter, say, of ice doesn't weigh as much as a cubic meter of liquid water. As a result, the ice is able to float on top because it's lighter. That has to do with those hydrogen bonds between water molecules. Here, in the liquid, you have water molecules getting a little closer to each other, forming all these hydrogen bonds, but they're getting in a little closer to each other. And as you cool the water off and it approaches crystalline form, the hydrogen bonds force the water molecules to spread out into this crystal lattice, and it has spaces in it. So it doesn't have as many water molecules in the same volume. 1 unit volume of ice doesn't have as many water molecules, and it doesn't weigh as much as the liquid form. Well, that's important if you're a polar bear. It gives you somewhere to live. So water has all these interesting properties, and these do a lot to explain why it's so important in life forms. Why it's really hard to imagine life not being based on water. Life as we understand it absolutely relies on water. So questions for me on that before I give you something to do? Okay then, I'm going to give you something to do. So let's try going back sharing again with my internet screen. There we are. And we look in our week 2 material, up near the top, right under the Cooper sodium, I have this thing called water errors. This is something I want everyone to take a look at, and I want you again broken out into small groups and talking this over. This will open up on your device just as a PDF. This is not something for you to turn in. This is not a homework. Just a thing for us to work on in the class, where it says practice only. Well, what I've got here is, and I don't know why it's got this annoying thing up. Okay. Sorry, I lost it. Let me try that again. Are you able to see the water error sheet now?
Yes.
Thank you. Well, what I have here is a paragraph, and it's giving a lot of information about water. Most of it's wrong. This is written by, say, someone who failed the class and didn't learn much about water. So imagine this is your friend's thing, and you're saying, oh no, that's terrible. Let me go through and make some corrections. This takes about 12 or 13 corrections to make it right. So what I want you to do is go through this line by line, sentence by sentence, and figure out what's wrong with it. I'm going to give you a few minutes, like 5 minutes in groups looking at this, and then I'm going to bring us back together and we'll walk through it and see if we can agree on what a correct version of it is. So you'll get that up around the top of the week 2 material under homepage. So I'm going to again break you out into groups.